Welcome to Making Sense of Mechanics, section 1.2. And in this section, we're really going to focus on what forces are and what kinds of forces we're likely to meet in A-level mechanics. But accompanying that, we're also going to think about what can we do in the classroom? How can we help students really clarify their thinking and talk carefully about forces? To begin with, I've chosen some definitions of forces that come up in the physics course, A-level physics, in specifications or revision guides. I found quite contrasting options. We'll have a quick look through three of those before we move on. So the first one, a force causes a mass to change motion. It's short, it's sweet, it doesn't really tell us too much. And if you're familiar with Newton's laws, you'll probably understand how this resonates with Newton's first law. Don't worry though, if you're new to mechanics and you don't know Newton's laws or you're not comfortable with them, they will get their own video in the future. You don't need to worry about them today as we talk about forces. So that's the first one. Number two, a force is defined as the rate of change of momentum of a body, or the product of a body's mass and its acceleration. Now, this is quite a formulaic, almost like an equation definition of force. But probably the frustration here is momentum. We have no idea what that is yet. And in fact, it's not in the maths course. You have to wait till further maths to study momentum. And even acceleration, because don't forget, I'm starting everything from the perspective of forces. And later we'll go into accelerations and motion. So that's not really fit for my purpose right now. But again, those of you familiar with Newton's laws will recognize Newton's second law in this. Number three, a force on a body is a push or a pull acting on the body from some external body. What I really like about this one is it references that external object, this other object, that is the cause of the force that we're thinking about. There is a connection that can be made here again with Newton's third law. As I've said, don't worry about those if you're not familiar with them. They'll all be discussed at the right time. So let's think about in the classroom. In the A-level maths classroom, what should we do? And let me say, this is what I currently do. As good teachers, we reflect on what we do. We iterate over time and improve. After around 10 years of teaching mechanics, this is good enough for me. A force is a pulling or a pushing action on an object caused by another object. Very similar to the third example that we just looked at. It is worth saying, remember that your students perhaps do A-level physics, and in that course they may be required to learn a specific definition. So we don't want to clash with that. And to be honest, in the maths classroom, we don't need this as a definition. It's just a sort of a working description, let's call it that, of what forces are. Pulls and pushes on an object caused by another object. While I'm here, I have got one mantra that I just need to get deeply ingrained in students, which is the following one. The only force we study that acts without physical contact is weight. Okay, sounds simple, sounds kind of obvious, hopefully, but it really helps clarify thinking later when we're studying which forces might be in play in a given situation. So the only force we study that acts without physical contact is weight. So remember, weight is the force due to gravity. We're on Earth, this massive planet underneath us. That force of gravity acts even if we're not touching the surface of the Earth, for example. And that's the only one we study. Obviously, there's things like magnets. They can exert force at a distance. They don't come into the mechanics course. I'll be mentioning this one several times during this session. The other thing we need to think about in the classroom is a clear and careful use of language. And I've got this structure that we're going to practice using for describing forces fully and carefully. And I recommend if you're new to mechanics, you'll be practicing this yourself, but definitely in the classroom with students, you'll probably want to push them to talk in this very structured way. Because if they can't, then you've got a clear indication that there's a misunderstanding or a misconception, they're missing something if they can't complete this pattern. So the structure is, there is a name of some kind of force acting on this object in some direction due to this other object. So we've got 4 gaps to fill in there for a full description of the action of a force. Let's show you a quick example of that in practice. So we've got a diagram of, this is a basketball floating in a bucket of water. Okay, it's the kind of fun stuff mechanics likes to study. 2 force arrows have been drawn. Going to start with my favourite one, because it's the only one that exists without physical contact. So how would I describe that? There is a weight force acting on the basketball vertically downwards due to the earth. Simple, full description. This other arrow, the blue one pointing upwards, there is a buoyancy force acting on the basketball vertically upwards due to the water. Let's think about physical contact. Apart from weight, every other force must exist because of physical contact. And the ball is only physically touching the water. So we've got a buoyancy force. The ball is not touching anything else. There can't be any more forces in play here. Let's take a look at the list of the most common types of force that students will be expected to know in mechanics problems. We'll run down them relatively quickly, and it might also be a good time to just bring in a couple of props, really simple things in the classroom. A cube, little cube, something light, something that's not round, it's not going to roll away or bounce. A colleague of mine used to have some fluffy dice at the back of their cupboard, and I could borrow one of those. This is just a lump of foam. All right, and force arrow, cardboard and gaffer tape. Okay, nothing fancy here, no expensive props, but it can be useful just for indicating forces as we talk about them. From the top, weight, the only force that exists without direct physical contact, and the weight force will always be vertically down towards earth. Then I've got this sort of generic pull or push. I could be pushing on the side of this block, or I could be pulling this side of the block, my hand doing some work there. Okay, so if I'm pulling on this block, then there'll be a pulling force to the right caused by my hand. Equally, if I'm pushing, there'll be a pushing force acting to the left due to my hand. Tension and thrust, they're sort of a pull or a push by proxy, in a sense. Now, sadly, I don't have any string at home. Imagine some string wrapped around this cube, and I can pull the string. So it's not me directly pulling the cube, I'm using the string to help me do that. We would say that there is tension in that string. So there would be a tension force acting to the right, would act along the string. If I pulled with the string in this direction, the tension force would also act in that direction. And a thrust is a push by proxy. Now obviously with a string, sounds obvious, I can't push with string, it would go slack. And that's important in the future. So we need a rigid object, something that we can push with, quite often called a rod in mechanics. I can use this as a push. So that would create a thrust force. We would say there's a thrust in the rod. That creates a thrust rod acting to the left on this cube. Let's keep going down the list. Normal reaction. Okay, the cube sitting on this table, supported by the table. There's going to be a normal reaction vertically upwards that's stopping this cube from basically falling, accelerating down to the ground. Friction. Friction's an interesting one because it doesn't act unless there's motion or an attempt at motion. Now we'll do friction fully in its own video. There's a lot of details to think about there, but right now, if the box is just sitting here minding its own business, there won't be a frictional force acting. If I come along and give it a push, then there'll be friction opposing me. And again, that will be a horizontal force due to the tabletop. And the other three on here, resistance, driving force, lift, I can't really demonstrate those with the cube, but resistance, air resistance. If you're driving your car down the road, there'll be a lot of air resistance against you. 90% say, probably more, mechanics questions completely ignore its effect. We set it to 0, we pretend it's not there. We neglect air resistance. But it can be a force mentioned in problems. So that's going to oppose the direction you're trying to move in. Driving force, also relevant for transport. It's the name we give to the force basically created by the engine of the car that allows it to accelerate forwards and actually get into motion. And finally, lift and buoyancy. We've seen an example of buoyancy with the basketball just a minute ago. And lift is a similar force. It's the force in the air that keeps aeroplanes up in the sky. All right, without lift, an aeroplane would just be a bus, I guess, driving along the ground. So that's a fairly exhaustive list of forces that you're likely to meet, and that can help in your descriptions. So I just want to run through an activity now that if you're new to mechanics, you'll want to practice this yourself, but definitely in the classroom, you'll need to be doing this with students. And here's an example diagram. This is from Pearson's textbook, just to acknowledge that. We've got a toy duck being pulled along by a string. 4 force arrows have been drawn on it. And the task as it was described in the exercise was to name these forces. Now already I want to extend that slightly. We're not just going to name them, we're going to describe them fully using that 4-block structure that I talked about before. The name of the force, the direction, what it's acting on, and what has caused it. You know where I'm going to start? C. It's the weight force. It's the only force that exists without direct physical contact. So I've described C as a weight force acting on the duck vertically downwards due to the earth. We've got A, B, and D. Might as well go in alphabetical order now. A going up. So A is the normal reaction force on the duck acting vertically upwards due to the ground. B. This is the frictional force. So it's a frictional force acting horizontally to the right on the duck due to the ground. And finally for D, we need to refer back to the story. This duck's being pulled along by a string, so there'll be tension in that string. So D is a tension force caused by the string acting on the duck, and it's in that direction, the direction of the string. Now you may have a couple of questions right now. Why is there just sort of one normal reaction pointing upwards at A when it's resting on several wheels? Or why is the frictional force pointing out the duck's back end, let's say? We're going to study force diagrams in our next section, okay? So we're going to look at those more carefully, we'll explain these issues, and that will also tie in with the beginning of our look at modelling assumptions, and these assumptions that we make when we simplify situations into mechanics problems. Just before I leave you though, I want to show you a dodgy example from the same book. We've got the situation, we've got a book resting on a table, 2 force arrows have been drawn. R's been described as a normal reaction on the book by the table. Fine, don't have an issue with that. It's this downwards arrow. It's labelled W, and it's been described as the force exerted on the table by the book. Now, there's nothing in there that's going to help your students right now, I would say. We're going to take that away. There are generous ways of trying to interpret that comment, but we're going to delete it. W will be the weight force on the book due to the earth. Completely different description. So if we think of those 2 arrows as forces on the book, one's caused by the table, it's the normal reaction up. One's caused by the earth, it's the weight force down. Now, there are forces acting on the table, that's true, but we'll study those more carefully, as I said, when we look at force diagrams in the next section. See you then.